All right, hello everyone. So we're actually going to start the very last section in chapter 2, which is the last section we're going to cover in this course. So we're going to start that today, and we'll finish it up next week. So this section is about pointwise and uniform convergence. But before we can quite get there, we're going to be talking about in this section sequences and series of functions. So before we've been talking about sequences and series of real numbers. Now we're going to talk about sequences and series of functions themselves. And so this is going to be a little bit different. And I'm going to, since we're going to kind of be doing this over 2 weeks, I'm going to split it up in a slightly different way from the way it's presented in the book. So the way it's presented in the book is sort of you talk about sequences and series, and you talk about pointwise and uniform convergence for them. And then there's this piece at the end that talks about Taylor series, because it turns out that pointwise and or uniform convergence of Taylor series is important to the study of Taylor series. What I'm going to do is this week I'm going to focus on sequences of functions and the kinds of things we can say about them. It turns out that some of those things just immediately generalize to series of functions, and I may just have you sort of work some of those out in the homework because the proof isn't very much different. But I'll save some of the discussion specifically about series, or some of the really more the emphasis on the series stuff will come when we talk about Taylor series. So you may not, as you're reading the book, you'll see all this stuff about sequences and series, and I'm just going to mostly focus on the sequence stuff for this week, and then we'll talk more about the series stuff next week. So I guess the first place to begin, right, is we need to sort of define what we mean by a sequence of functions. In some sense, it's exactly what you think it is, but we have to be a little bit careful. So definition. So let Fn from some domain D into R for every natural number n be a collection of functions with a common domain. Domain D. Okay, so the first thing to recognize here is that, and to be careful of, is that when we're talking about a we haven't actually done it here yet, but when we finish this definition of a sequence, every function in this sequence has to have the same domain. Otherwise, if your domain is shifting around and changing with n, you're going to have a lot of issues. And so essentially we say everything has to have the same domain because that makes life work out a little bit better. So then a sequence, or f sub n, forms a sequence of functions. And similarly, if we can talk about a sequence, we can talk about a series. All right, the sum f sub n of x forms a series of functions. And again, this is where when we start next week, we'll really get into sort of Taylor series, which is a big place where these come up. Obviously, there are lots of other types of series of functions you can talk about that are very important in different applied settings. So Fourier series, for example, would be another sort of common one you would see in certain disciplines. So a couple of things. So we've defined sequences and series of these things. The first thing we're going to have to sort of worry about potentially is, does talking about convergence make any sense at all? Because normally, right, if we're going to define a sequence or a series of something, we need to think about what it means for that sequence or series to converge to something. So we need to talk about that. And so moving towards that, then the first thing we often try to think about, right, is can I go back and just rely on maybe something I knew about sequences and series of real numbers? And so you can imagine, so let's say we have, and I'm just going to sort of draw this in R2. So you can imagine, let me take the following. I'm going to take f sub n of x to be x to the n. So again, if I wanted to write this out another way, you can think of this as the sequence of functions, which is x, x squared, x cubed, x to the fourth, so on and so on. And I'm going to take these on the domain 0, 1. Make this nice and easy so I can draw this. So put two very important points here. All right, so I can start drawing these, right? So this is f1 of x, and there's f2 of x, the f3 of x, and so on and so on. Now, if I fix an x value, so this is the first thing I want to emphasize. If I fix an x value here, okay, so here's some fixed value, x is equal to a, and now I look at this, the sequence f sub n evaluated at a, this is now just a sequence of real numbers, right? So this is then now just the sequence a squared, a cubed, so on and so on. And really, what I can think about here is, right, visually I'm sort of looking at, so here's, this height is f1 of a, this height is f2 of a, this height is f3 of a, so on and so on and so on. And now, right, if I look at this, it's clear that, at least for this a value I've chosen here, right, that as my n is going off to infinity, my f sub n of a is converging, and it looks here, right, like I'm converging to 0. Now, of course, it's possible, maybe not in this example, but we'll look at this example more in a minute, right? It's possible, of course, as I change my x, that could also, whether or not I converge, and if I do converge, what I converge to may change as I change this x value. But my point here is that if I fix a particular x value, then this is now just a sequence of real numbers, and I know how to talk about convergence of sequences of real numbers. Okay, so sort of immediately we can say, okay, if I have a series of a sequence of functions, I can look at that sequence of functions, fix a particular x value, and ask the question, for that particular x value, does this sequence converge? Okay. And that's all sort of stuff we've looked at before. And so this is sort of precisely what we call pointwise convergence. Let's write a definition out here. Definition: a sequence of functions. And so I'm not going to continue writing sequence of functions. When we're referring to the sequence of functions, I'm just going to write something like this, and I'm not going to put the of x. So I'm just going to write a sequence and then fn converges pointwise on a set A, if and only if, for each little a in A, the sequence f sub n evaluated at A converges. Again, what are we saying here? We're saying that this sequence converges pointwise, and we can talk about it on a set, or we could just think about at some point A in the domain. If the sequence where I take the functions and evaluate each of the functions in the sequence at A, that creates a sequence of constants, or a sequence of real numbers. if that sequence converges. Right? So what I'm going to do is actually I want to switch over here to the computer for a second. And because my camera is sitting on a tripod, I'm going to actually just turn my camera off. Otherwise, you're just going to be looking at the top of my head. And turn that off. And I'm going to share my screen now. So let's share Desmos. There we go. All right. So I just sort of want to give you a, sorry, let me fix something real quick. All right, there we go. So what I want to do here, you should be able to see my screen now. And so I'm going to start here. I've just got the same sequence of functions that I had before. And what I've done is I plotted the first, second, third, fourth, fifth, sixth, 10th, and 100th functions in this sort of sequence. And so again, just to sort of give you an idea of what's going on down here, and sort of, you can ignore the stuff over on the left. I mean, at least that's not my focus, or what I want you focused on necessarily. So you notice that if I'm in here, and if I fix any particular x value in the interval 0, 1, so maybe I fix the x value at 0.4, right? Now I can look at, right, each of these heights. And so f1 of 0.4 is just 0.4, but f2 of 0.4 is 0.16, f3 of 0.4 is 0.064, and so you can see, right, these heights are converging, and at least visually, right, I feel fairly convinced that this is going down to 0. Okay. Now, I can also ask the question, so certainly I now believe that it is converging pointwise when x is equal to 0.4, and it's converging to 0. But then I could change the x value, and I could ask the question, well, what happens at that point? Right, so if I change the x value, I don't know, over to 0.6, what happens? Well, we look at this and you say, okay, those heights are 0.6, 0.36, 0.216, 0.1296. Okay, you know, as I go for it, it looks like these are all decreasing and they're going to 0. And so as you play around with this, you might sort of start to conjecture that no matter what x value you choose, that you're going to converge to 0. But you would be almost completely right. But of course, my domain, remember, I took to include the 0.1. Well, if I go over here to the 0.1, then I could ask myself, what happens at 1? Well, at 1, every one of these is going to evaluate to 1. So when x is equal to 1, f sub 1 of 1 is 1, f sub 2 of 1 is 1, f sub 3 of 1 is 1. So for every x value starting at 0 and going up to 1, but not including 1, these heights are all converging to 0, but here it's converging to 1. So this function, so let me actually flip back over. Let me stop my share and flip back over to the board here. So if I'm looking here then at this example, I could then ask sort of for each x value, can I plot what the limit is? So for every one of these x values starting at 0 and going up to 1, but not including 1, my function is converging pointwise to 0. But at 1, it's converging pointwise to 1. Okay. So this sequence of functions converges pointwise at every point in its domain for every x value. And so we might say something like fn converges to the function 0 if 0 is less than or equal to x is less than 1, and 1 if x is equal to 1. Sorry if you hear my thing, my wife is texting somebody in a group chat, and anyway, it's just dinging and dinging. I need to figure out how to turn that off. In any event, my sequence of fn sort of converges in this way. Sorry, I should say here, fn of x, right, converges here. And what you converge to depends on what x value you're looking at. Okay, all right. So I'll make one more observation here, and then we'll sort of move on to another example. The observation I want to make here is that if you look at each of these f sub n's, and you fix a particular n value, each of these is a continuous function, right? X is a continuous function, x squared is a continuous function, x cubed is a continuous function, x to the fourth, x to the fifth, you get the idea. All of these are continuous functions. And each of them, and this sequence of functions converges pointwise, but the limit is not a continuous function, right? This green function here sort of is not a continuous function. So while we can talk about sort of convergence in this way, in this sort of pointwise manner, you can't expect that properties like continuity are preserved as that sequence converges, right? So that's kind of not great, right? I mean, I'd like to think that sort of limiting processes preserve certain things, but here's an example of a limiting process where we take a sequence of continuous functions. Each of these functions is continuous. Its pointwise limit is not continuous, however. Okay, and what we're going to see actually is that, well, yeah, pointwise convergence, you really shouldn't expect much of anything is preserved, and we'll see that through a couple other examples. All right, so let me switch back over here to Desmos. I want to look at a couple of other interesting things that are going on here. All right, so I'm going to come over here and I'm just going to change the functions I'm looking at. I'll take this one next. Oh, sorry, I want to look at this one. Sorry. Zoom out here some now. And let me turn this off for a second. Sorry, give me 1 second. I'm just trying to fix one thing real quick. All right, sorry, I actually paused the recording there for a second to fix. I just grabbed the wrong example. So I want to look at another sequence of functions here. And this one is sort of, let me maybe sort of describe it conceptually first before we worry about, and it doesn't really matter here what actually the equation is, although this is example 2.24 from the book, so you can go and look at it there. But the idea is I'm going to construct a sequence of functions that are sort of these triangle functions. So the sequence of functions is often referred to as sort of marching triangles. So my sort of goal here is that each of these triangles will have area 1/2. Okay, and so if you notice here, and I can zoom in a little bit, so this triangle has height 1 and base 1. And so this is the first function in my sequence, and then it's 0 outside here. Okay, and then the second thing in my sequence, so sorry. This has a base 1 and height 1, so the area is 1 times, or 1/2 times 1 times 1, so the area is 1/2. Here's another one. Okay, this has, you'll notice, has height 2 but base 1/2, so its area is 1/2 times 2 times 1/2, which is just again 1/2. Okay, and so what I do is I write out this sequence of functions, and I can do this by just kind of creating lines where it goes from 0 up to a peak, which has height n, and it has a base that is width 1/n. So you'll notice that this third triangle in black here it has a height of 3 and a base of 1/3. Okay, and so I can sort of keep constructing this sequence of, and it's going to look very sort of, it's going to be a little hard to look at, but let me fix this here. So I want to go between 0 and 1. I want my y-axis to be allowed to get very large. So eventually I'm going to want that to be pretty high, but let me just go maybe 30. All right, so you can sort of see here these functions. And so, right, the triangles keep getting larger, and eventually that one's almost off the screen. And so you can look at these, and let's sort of fix an x value and see what happens. Well, if I fix a particular x value, let's move my green x value along here. So let's say fix an x value here. Then what's going to happen? Well, you see they're sort of decreasing, and then eventually they become 0. And you might ask, well, why do they eventually become 0? Well, right, any x value I pick, eventually the base of the triangle is going to get smaller than that x value, because the base of my triangle is only 1 over n, only has width 1 over n. So eventually n is going to get so large that it's just 0 out here. So it actually turns out that for any x value you pick, this is converging pointwise to 0. Okay. So here you have an example, and let me maybe switch back to the board here. I think this is worth so if I sort of write these out just so you can see this, right? This is f sub n of x is equal to, this is 2n squared x when 0 is less than or equal to x is less than 1 over n. This is 2n times 1 minus nx when, or sorry, this is 1 over 2n when I'm between 2n and 1 over n, and then it's just 0 when x is bigger than 1 over n. Okay. So this is the sequence of functions, and when I draw them, right, I get these triangles. So here's one. So the first is a triangle that, say, and my scales aren't going to have sort of the same. So here's my first one. Okay. My second one will have height 2, but base 1/2. So it's going to look something more like this. My third one will have height 3, but base 1/3. So maybe it'll look something like this, but you get the idea here. So fix any x value you want. Okay. Eventually, right, because the base of these triangles is going 1, 1/2, 1/3, 1/4, 1/5. Eventually, you're going to get far enough out that this is just going to be 0, because it's going to be in sort of this piece where your function is 0. Okay. So this sequence of functions, f sub n of x, it actually converges to 0, pointwise. Okay. And so, you can look at this and you could go, oh, well, these are all continuous functions. They actually have a nice continuous limit. F sub n of x is converging to 0, right? This is a nice continuous function. But there's still other properties that are not preserved. So, for example, if I look at the integral of each of these functions, let's see what's going to happen. So imagine I look at the integral, and we can just work on this from 0 to 1, because all of these functions are 0 outside of there. So if I look on the interval 0, 1, and I look at the integral of any one of these functions, f sub n of x, right, I constructed these specifically so that the area of each of these triangles is 1/2, right? So there's a base 1, height 1, it's 1/2. So the integral of each of these f sub n of x's is 1/2. But look at what happens if I look at the limit function. So I'm just going to call that f of x. I'm imagining here that this is my f of x. Well, that's the integral of the zero function. That's just 0. So what's happening here is that even though these are converging pointwise, this is a sequence of continuous functions which is converging pointwise to a continuous function, which doesn't always happen, but in this case it is. But still, I have a problem here because the integrals are not converging, right? So, and even though this looks complicated, right, I'm really just thinking, right, this is a sequence of real numbers that's just the integral of each of those functions. And each of these is 1/2, 1/2, 1/2, 1/2, 1/2. When you get to the limit function, that integral is 0. And so again, it's sort of, again, this example that things that are sort of nice that you would like to be preserved when these sequences converge, they're not always preserved. Okay. And so what we want to work on is trying to understand under what conditions we might expect. Certainly, I guess my point here is that pointwise convergence is not enough to guarantee that any nice properties of functions are preserved, right? We've already seen that I could have a sequence of continuous functions converging pointwise, but that won't be enough to get to ensure that my limit function is also continuous. Here I have a sequence of integrable functions, right? Each of these is integrable. And the sequence of integral values converges. It converges to 1/2, but that's not the integral of the limit function. And that's, again, sort of not nice. I'd like these things to be true. And so I need something more, obviously, than pointwise convergence. Pointwise convergence isn't enough. Okay? And so this is where I need something better. Okay? And that better thing is going to be uniform convergence. Sure, I do this in the same way the book does it. A sequence of functions then converges uniformly to a function f on a set A if and only if for every epsilon greater than 0 there exists a natural number n so that whenever little n is greater than capital N, then f sub n of x minus f of x is less than epsilon for every x in A. So let's sort of talk about this, because I think on the surface, and the first time you see it, you go, this is just like pointwise convergence, and you've just written the epsilon delta definition. But that's not quite true, and we need to carefully look at why. So the sort of important piece here is that this definition requires that fn of x minus f of x get close, or sorry, fn of x and f of x get close to each other, arbitrarily close to each other, for every x in my set. Okay, so when we're looking at pointwise convergence, like, let's just go back to this example of x to the n. So you might have said, well, yeah, each of these is getting close, and sort of individually they are, but right, no matter how close, how quickly this sequence is going to 0 here, there's sort of points way over here that are very close to 1 that still are not getting close to 0, or at least certainly aren't getting close at the same time that these points over here are getting close. So what uniform convergence, so this definition says converges uniformly, but uniform convergence is another way of saying that, right? Well, the definition of uniform convergence is saying is that if something converges uniformly, then I ought to be able to choose a capital N that doesn't depend on X, right? The N only changes with respect to epsilon. So I ought to be able to choose a capital N that's independent of X, so that whenever I go out far enough in this sequence, all of my X values will be within epsilon. All of my F sub N of X values will be within epsilon of F of X. So it's sort of requiring that it can't just be that some points are getting close right now and some points maybe will get close later. This is sort of like saying all of the points must get close at the same time. And that's more demanding than pointwise convergence. Pointwise convergence just says at any particular point, you will eventually get close. But now uniform convergence is sort of saying, well, it's not enough for them all to get close individually. They all have to be getting close together at the same time. And because this is a more stringent requirement, so for example, we showed that this converges pointwise to this function, but it does not converge uniformly. Okay, and so since it does not converge uniformly, we see that uniform convergence must be a stronger condition, right? Uniform convergence, and we can sort of understand that from the definition. But uniform convergence is sort of a higher bar, but along with that higher bar, we might expect then that it preserves more things, right? It's a harder condition to meet, but then once you meet this higher condition, you may sort of get some extra properties that follow, and that's exactly what we're going to see. Okay. So let's look at that. And so the first theorem we're going to prove is sort of exactly the kind of theorem we wanted something better for. So this is theorem, sorry, let me just make sure I give you the right number from the book. This is theorem 2.66. If a sequence of continuous functions converges uniformly on a set, then the limit function is also continuous on that set. So what does this say? This essentially says uniform convergence preserves continuity. If each of the functions in your sequence is continuous and they converge uniformly, then that limit function must be continuous. Okay, and so let's set about proving this. Okay, so maybe I'll start down here and just set up some of the problem. All right, so let Fn be a sequence of functions, or a sequence of continuous functions on a set A. Okay, so this is just sort of setting up some of my stuff here. Oh, sorry, and let Fn converge uniformly to, and I'm going to just call that limit function F. All right. So if we want to show that the limit is, this limit function F is continuous, then what I want to do, so I'm going to need an epsilon. So let epsilon greater than 0 be given. And let me take a to be little a to be some point in my set capital A. Okay, so just as a note here, and so what do I want to show? Then I want to show that I can choose delta greater than 0 so that whenever whenever x minus a is less than delta, then f of x minus f of a is less than epsilon. This is my goal. So I mean, this is not part of my proof, but just as I'm thinking here, sort of what's my goal? I want to show that I can choose a delta so that whenever x minus a is less than delta, then f of x minus f of a will be less than epsilon. Okay. All right. So let's try to do that. Now, since I'm sort of writing this as a proof, so let epsilon greater than 0, let a be greater, or let a be in A. Let me extend what I want to show here. Sorry, I want to sort of give you a game plan of this so the proof doesn't seem totally out of left field, right? So I want to show this. So what I'm going to do is I'm going to add and subtract a whole bunch of things. Right. So I can rewrite this difference here as this, and you're going, oh my God, why would you ever do that? And then eventually what I'll do is I'll apply the triangle inequality, so I'll get less than this. And we'll go back through this in a minute, but just to give you the idea. So the idea is going to be, what I know is that this sequence of functions, I know two things about it. I know that each of these is continuous, and I know that they converge uniformly. So breaking it up in this way, what I'm going to be able to do is the following. I'll be able to control this term. Notice that here, now I have both x's, right? So the only difference here is that this is an element of my sequence and this is the limit function. I can control this using the uniform convergence. Similarly, I'll be able, these are almost identical, except this one has x and this has a. So I'll also be able to control this using uniform convergence. And now this middle term, I'll be able to control using the continuity of f sub n, right? So I know that each of these f sub n's is continuous, but I'll be able to control this by the continuity of f sub n. So I'll be able to make this term as small as I want, this term as small as I want, and this term as small as I want, so that eventually this whole difference will be less than epsilon. Okay? So this is sort of the idea. This looks terrible, right? But there's sort of a reason why I'm gonna break it up in this way. But we'll see that in a minute. All right. So as I'm writing my proof, right, and again, this black box here sort of isn't the proof. That's just a thought there. I'm going to proceed. So I've got epsilon greater than 0, and I've got a point A in my set A. So since f sub n converges uniformly to f, well, now I'm going to go back to the definition. Okay, what does that mean? That means there is a capital N in the set of natural numbers such that for all n greater than capital N, f sub n of x minus f of x can be made as small as I want. And in this case, I'm going to make it less than epsilon over 3. Okay, and we'll see why that works out nicely in a minute. Okay, but I can make it as small as I want, so that this is less than epsilon over 3. And again, the extra piece for uniform convergence is that this holds for all x in A. All right, so that is true by uniform convergence. Okay. Now, the other thing I need to think about is how I'm going to use the sort of continuity, and I'm going to need to do that in a minute. But first, let me fix some value of m greater than this capital N. Okay, and so this is how the book actually writes it. I'm going to do it in a slightly different way. Instead of taking some m and introducing another variable, I'm going to consider f sub capital N plus 1. Right? So now why am I doing this? Because I know that capital N plus 1 is bigger than n. So I know that f sub capital N plus 1 of x minus f of x in absolute values is less than epsilon over 3 for all x in A. And that gives me a very specific sort of thing to work with here. Okay. Since f sub n plus 1 is continuous, right, it's an element of my sequence. Each thing in my sequence is continuous. So consider this particular function. And since it is continuous, I can choose a delta greater than 0 so that f sub n plus 1 of x minus f sub n plus 1 of A can be made as small as I like whenever x minus A is less than delta. And so here I'm taking advantage of the continuity of f sub capital N plus 1. Okay. So I'm almost done. Now I need to just combine all of these pieces of information. Then for any x in A with x minus A less than delta, well, let me look at f of x minus f of A now. Remember, my goal is to show that when x minus A is less than delta, then f of x minus f of A can be made less than epsilon. And so now this is where I'm going to employ this idea from before. So I have f of x minus f sub, and now I don't just need a generic n, I need an n plus 1 here of x plus f minus n plus 1 A plus f sub n plus 1 of A minus f of A. Sorry, I had to break that up on the 2 lines there. Okay, and now I can apply the triangle inequality. So this is f of x minus f n plus 1 of x plus f sub n plus 1 of x minus f sub n plus 1 of A plus f sub n plus 1 of A minus f of A. Now, what do I have? All right. Looking at this first term, since why did I choose this to be n plus 1? Because n plus 1 is greater than capital N. And when I'm looking at something that's greater than capital N, then f sub capital N plus 1 of x minus f of x must be less than epsilon over 3 for every x value in A. So it's certainly true here, and it's also true here because both x and a are in my set A. So each of these things can be made less than epsilon over 3 using the uniform convergence. So the uniform convergence takes care of these two outside terms. Now I turn my attention to this inner term here, and this is where I'm going to use the continuity of f sub capital N plus 1. So since f sub capital N plus 1 is continuous, I said over here I chose this delta so that this difference would be less than epsilon over 3 when x minus a was less than delta. And well, x minus a is less than delta. So this difference must be less than epsilon over 3. And now you see why I chose these to be epsilon over 3 as opposed to epsilon or epsilon over 5 or something like this, because now I get that this is equal to epsilon. And so what have I shown? I've shown that for any x in a, when x minus a is less than delta, then f of x minus f of a in absolute values is less than epsilon, okay, which is exactly what I want. And this proves that this function f must be continuous. Okay. And so sort of the idea, right, is to, you sort of get close, you go far enough out in your sequence that you know you're close to your function f, so that essentially these two terms say, don't worry, you're not too far away from f, but now you can work on one of the elements of your sequence and not on the limit function itself. And that's sort of the power of this proof. This is a really, well, this is a sort of a favorite proof of mine in all of analysis, really, because it's sort of fundamental to this idea of why uniform convergence is important. So yeah, the other thing let me emphasize, right, is that this only worked because of uniform convergence, right? I was able to choose a capital N that worked for both A and X, right? That allowed me to make both of these terms small at the same time. If I only have pointwise convergence, this fails because I can't guarantee that I can sort of get both of these within epsilon over 3 at the same time. And so if I can't do that, then this sort of falls apart. But with uniform convergence, again, I know these are getting close sort of at the same time, and I can take advantage of that and then just work on f sub capital N plus 1, which is one of the elements of my sequence. And so I know that, for example, it's continuous. All right, great. So that's theorem 2.66. Theorem 2.67 actually says, sort of, if we're kind of looking back at the examples we did, that if you have a sequence of functions which is converging uniformly on an interval AB, then the limit of the integrals is the integral of the limit function. Okay, so let's sort of carefully write out this theorem. So that this is going to say that not only is continuity preserved, but also the values of integrals are well, they're not preserved, but they converge according to the same way the function converges. All right. And actually, the proof I think of this is quite a bit more straightforward. This theorem 2.67. If a sequence Fn of continuous functions converges uniformly, and let's do this on the interval AB, then the limit as n goes to infinity of the integral from a to b of f sub n of x dx is equal to the integral from a to b of the limit as n goes to infinity of f sub n of x dx. Okay. So again, let's sort of appreciate what's going on here. this is saying that if your sequence of continuous functions converges uniformly on this interval, then if I look at the integral of each of the individual functions in my sequence and take the limit of those, that will be the same as if I just took the limit of my function and integrated that thing from a to b. Okay, so what this is sort of saying is that this limiting operation and this integral, which we should note is also really a limiting operation, if the sequence of functions converges uniformly, you can interchange these two limiting operations. Okay? It's really a powerful thing to have at your disposal in analysis, the ability to switch limiting operations. But we have to note, right, and we did earlier, right, that this isn't always the case. So that sequence of sort of marching triangle shows you that it's not always the case that you can do this with a sequence of functions. But if you know that the sequence of continuous functions converges uniformly, then you know you can, in fact, switch these. Okay. Again, the proof of this, I think, is actually quite a bit more straightforward. So here's the proof. So let Fn be a sequence of continuous functions. And I'm going to abbreviate some of this. Converging uniformly to a limit f. Okay. Converging uniformly to a limit on AB. All right, let epsilon greater than 0 be given. Okay, so now what do we know? We know these functions are, each of the fn's are continuous, okay, and we also know that they're converging uniformly, okay. So let's sort of make use of each of those pieces. So the first thing is sort of just definitionally, if we're looking at this, this is what we want to show. Each of the fn's is continuous, so we know they're integrable. So for example, this sequence here is well defined, right? Each of these integrals is well defined, and that's good, that's important. And in particular, one thing we're going to make use of is, let's note that f is also continuous. Now, how do I know that? Well, I have a sequence of continuous functions that's converging uniformly. Theorem 2.66 tells me the limit must also be continuous. And so since f is continuous, so note that f is continuous, so that if I look at the difference, f sub n minus f is continuous. On AB. Okay. So f sub n's are all continuous, therefore they're integrable. F is continuous, therefore it's integrable. All right. And so now I sort of have that both sides of this thing are well defined. Now I just need to show they're equal. I'm going to do this by looking at their difference and showing that I can make that difference be 0, essentially. Okay. All right. Let me take advantage now first of the uniform convergence. So since f sub n converges to f uniformly, there exists a capital N in the natural numbers, so that when n is greater than capital N, we have that f sub n of x minus f of x is less than, and I can make it as small as I want. I'm going to make it less than epsilon over b minus a for all x in my set A. Sorry, I'm getting sort of down in the corner of the board there. Okay. So this is, again, just a statement of what it means for something to converge uniformly, where I can choose a capital N so that when I go beyond that capital N in my sequence, f sub n of x minus f of x can be made as small as I would like. In this case, I want to make it smaller than epsilon over b minus a when for all x and a. Okay. So let me erase this. All right, so again, I want to take something beyond n, but in this case, I don't want to fix a specific thing. So just let, in general, little n be something beyond capital N. And then, I want to look at the difference between the integral from a to b of f sub n of x dx and the integral from a to b of f dx. Now, I can use properties of integrals, right? This is just the integral from a to b. Since both of these are integrable, this is the integral of the difference. So it's just applying a property of integrals that we've looked at before. Okay. And now this is, here's another property of integrals we had. This is less than or equal to the integral from a to b of, I can push the absolute values inside. But this is essentially, right, like the integral version of a triangle inequality, right? If you add a whole bunch of things up and then take an absolute value that's less than or equal to taking the absolute value of each of them and then adding them all up. This is the integral version of the triangle inequality, essentially. But now I know that I can make this thing less than, this difference I can make less than epsilon over b minus a. And now this is a constant, so if I integrate a constant from a to b, I just get that constant times b minus a, but in this case, that's just comes out to be epsilon. So I can make this difference less than epsilon, and I can do this for every n greater than capital N, not just for one of them, but I can do it for everyone. And since I can make this difference less than epsilon over b minus a for every n beyond here, myself, I just need a little more room, then, well, if I look at this thing, right, this really is the integral from a to b of the limit of f sub n, right? Because that's what f was defined to be. So then, if I can make this difference 0, this tells me that the limit as n goes to infinity of this thing is equal to this thing, but by definition, drop the of x there. But this thing by definition is f of x was defined to be the limit as n goes to infinity of f sub n of x dx. So this result is exactly what I want. So again, what is this saying? If I have a sequence of continuous functions converging uniformly, sort of integrals will play nicely, right, with both the functions in the sequence and the limit itself, right? You'll get behavior that's sort of ideal. Okay. So I'm going to stop the video for there today, but I want to encourage you to do, well, I mean, you should always be reading the section, but I would encourage you to look at example 2.25. So what example 2.25 essentially shows you is that differentiability doesn't play quite as nicely. Essentially, if I have a sequence of functions that converge, a sequence of differentiable functions that converge uniformly on some interval, I can't expect that their derivatives will play nicely without some additional conditions. And then theorem 2.68 gets into that. We will actually start looking at that next time, and we'll also start talking about series of functions because we'll be looking at Taylor series, and that'll provide some really nice examples to see, in some sense, where these things can go wrong. But it also gives us some really nice specific examples of sequences so that we can play around with those more. So we'll stop there for today. or really for this week, and take a look at the homework, and I'll have some problems there for you.